Thank you for joining us this morning, and welcome to the 7th Annual Toronto Machine Learning Summit. I see that folks are just streaming in, so we welcome everyone for this morning kickoff session. I hope everyone can hear me and see me okay. We have a very special guest this morning, which we'll get to. I do want to start with the land acknowledgement. So we acknowledge that as I'm based here in Toronto, this sacred land on which Toronto operates is the territory of the Huron-Wendat, the Petun First Nations, the Seneca, and most recently the Mississaugas of the Credit River. Today, the meeting place of Toronto is still home to many Indigenous people from across Turtle Island. And we're very grateful to have the opportunity to work on this land in this territory within this community. So with that being said, thank you, everyone. Please let me know if you can hear me okay. I'll just wait. Yeah, awesome. Thank you, Sergey. We have a very special guest this morning. He is, in part, one of the major inspirations and the reasons why the Toronto Machine Learning Summit started many years ago, and it's through his work that has inspired so many people within our community. So it's an absolute pleasure to have our first guest. He's recognized worldwide as one of the leading experts in artificial intelligence. Professor Yoshua Bengio is most known for his pioneering work in deep learning, earning him the 2018 AM Turing Award, the Nobel Prize of Computing, as most of you are probably aware. This was alongside Professor Jeffrey Hinton and Yann LeCun. He is a full professor at the University of Montreal and the founder and scientific director of MILA, the Quebec AI Institute. He co-directs the CFAR Learning and Machines and Brains program as senior fellow and acts as the scientific director of IVADO. In 2019, he was awarded the prestigious Killam Prize, and in 2022, he became the computer scientist with the highest H-index in the world. He is a fellow of both the Royal Society of London and Canada, Knight of the Legion of Honor of France, and Officer of the Order of Canada. Also concerned about the social impact of AI and the objective that AI benefits all, he actively contributes to the Montreal Declaration for the Responsible Development of Artificial Intelligence. So we will be joined by Professor Bengio, a friend and colleague, Andrew Brown, who's been a big supporter of TMLS, will also help field some questions towards the end. I know Professor Bengio will also answer a couple questions about AI safety and fairness towards the end as well. So thank you so much. I really hope you enjoy. I look forward to seeing you in person at the Toronto Machine Learning Summit tomorrow and the day after. But in the meantime, please join me in welcoming Professor Yoshua Bengio. Thank you.
Thank you, Dave. Thanks for having invited me. Let me try to share my screen. Okay, so today I'd like to tell you about how the amazing advances that many of you have seen in deep learning with large language models, the scaling effect of large neural nets could be put to use in a very uncommon perspective of machine learning, which I call model-based machine learning, which is relying on new kinds of reinforcement learning / generative models that I'll briefly talk about. Okay, let's see if I can change slide. Yes. So model-based machine learning, I'll explain more, but basically it's the idea that we're gonna do like what scientists do, in which we separate the understanding of how the world works, that's the model, from how we answer questions. Right now, if you look at ChatGPT, for example, there's one neural net. It does both things. It has incorporated implicitly knowledge about the world, and it answers questions. And I'll argue this is not necessarily the optimal thing. Also, having a model is something that matches well what we know about humans. We can imagine things that haven't happened. We can imagine counterfactuals. We also have abstractions in our way of modeling the world, and there's a lot of evidence about that. Of course, that you can just think for yourself, but also from neuroscience. There's a kind of bottleneck of information in working memory in the brain, where only a few bits of information go through. Has been a lot of inspiration for my own work. Now, one thing I'll talk about is that when we separate the model part from the inference or question answering part, there is an advantage in terms of capacity control. Briefly, the model could be small because maybe you don't need a lot of equations or bits of information to describe, say, causal structure in the world. But in general, answering questions like doing inference requires a lot of degrees of freedom to do it right. When we train that inference part, it's not limited with a model-based approach. It's not limited by the amount of data we have. So if we don't have a lot of data, we can have a small model, but we still have a very big inference machine. And I'll give examples of that. And the reason this is possible is because the inference machine, to train it, just needs to query the world model. So think of like the world model is like a simulation or something that allows us to get an answer about how things would happen. And the inference machine is trying to get answers to questions and can learn to do that by trying things out in the machine's mind without having to rely on a limited amount of data. Okay, so let me dig a little bit more into this. When we separate the model part from the inference part, so the model part, again, I'm going to give like more concrete examples. Say, think about learning to play the game of Go. Well, what is the knowledge that we need about how playing Go works? Like essentially, it's the rules of the game. How many points you get for doing this or that, and what is allowed, what is not allowed. And the rules of the game in Go are very simple. There are 9 rules. You can write them in a single page, and it's a very small piece of code. On the other hand, even if you know the rules, and that's the model part, like the world knowledge, how do you answer questions like, how do I win? What should I play now? That's the inference part. And we know actually the exact inference in the case of Go is intractable. You would need a huge amount of computation to get the best possible answer to the question. But you can approximate it, and that's what people have done with AlphaGo, with DeepMind. And we know that in order to succeed there, you need very, very large neural nets because inference is difficult. It's trying to approximate a computation that is NP-hard, that is intractable. And so we see in this example that there's a huge mismatch between the optimal capacity, how many bits of information do I need to describe how the world works, what are the rules of the game, and how many bits of information do I need to describe how I do things in the world, how I answer questions, how I do inference. And so my point here is that when we have a single neural net that does everything, it's going to be in trouble because whatever we choose for the capacity of that neural net is going to be generally too big for the modeling how the world works. So it's going to overfit the information from the data. And it's going to be too small for the inference part. It's going to underfit the task of how to answer questions. So yeah, and the basics of learning theory is that the capacity, like the size of a model, of a neural net or whatever machine learning system should be proportional to the amount of data that is available to train it. And so this mismatch could be a serious problem. So what can we do? Well, I'm going to suggest that there's a way to do that. In fact, it's not a new idea. Model-based reinforcement learning has been around for like 40 years. Now, let me now go a little bit deeper into how we're going to get our model. So the standard way of training a model in a model-based approach is with maximum likelihood. And in fact, this may be one of the reasons why this whole model-based approach never worked really very well. Okay, so what's the problem with maximum likelihood? Well, what you're trying to do is to find, if you think of, like, again, go back to how scientists think about things, and I like to do that. a model that fits the data is like a theory that explains the data. And in general, there'll be many theories that could fit the data, and you pick one. So in maximum likelihood, we pick a setting of the parameters of a neural net, for example, that minimizes the error, the prediction error that fits the data as well as possible. But there could have been other settings of the neural net that also fit the data. How could that be a problem? Well, we see that in large language models like ChatGPT that are saying things that are wrong with very high confidence. So people call that hallucinations. This is a serious problem in practice because you don't want your AI system to confidently take decisions that are really dangerous. So that's the main problem, and it gets worse if you then, in the model-based approach, we train somehow a model, and then we train an inference machine that is used to answer questions that are consistent with the model. But like, think of the Go playing policy, right? But if the model is wrong, at least in some places, then when we optimize something wrong, I mean, even if it's like slightly wrong, it's like the optimization is going to focus on the places where it's very wrong. Like the model is going to discover some configurations, some paths, some decisions that look incredibly good, but actually could be pretty bad. And that's another way of talking about hallucinations, except now we're optimizing for these things, and then it can get so bad that the model-free approach, like the current state of the art in deep learning and reinforcement learning, is usually preferable to this. Okay, so what's the alternative? Well, the alternative is, like, again, as I said, that's how scientists do it. They try to maintain not just one theory, but multiple theories that are consistent with the data. And let's see how this could be advantageous. So imagine this situation here with this robot in front of two doors. And based on the data that it has seen before, it has two theories. And both theories are compatible with previous data. But they say very different things in this case. So the first theory on the left says, if you go on the left door, you die. If you take the right door, you get some cake. The second theory on the right says, if you take the left door, you get some cake. If you take the right door, nothing good, nothing bad. Okay. If you were to pick one of those theories kind of randomly, because they both could do maximum likelihood, you might be unlucky and pick the wrong one. So, for example, maybe the right one is the left one. You pick the second one, and it says go left because there's some cake, and then you die. That's bad. What's the alternative? Well, the alternative is to maintain both theories in your mind in some sense, and notice that, well, there's 50% chance it could be either. So what should I do? Well, I should obviously take the right door, because there at least I don't die, and maybe I'm going to get some cake, right? Whereas the left door, I get some cake or I could die. The dying is so bad that you don't want that. So that's what it means to be Bayesian. Being Bayesian means you want to maintain a distribution over all the theories, all the explanations. Okay, and there's also a lot of theory that in a way it's the most rational way to take decisions. Unfortunately, why is it that not all machine learning is Bayesian? Because it requires computations that are intractable. The posteriors, the normalizing constants, the sums, the marginalization that have to be done, they're too expensive. So a very important message of my talk is that with the advances we've had in recent years with large neural nets, we can actually do a good job of approximating these intractable posteriors that are needed in Bayesian calculations. And the reason it works is because these really large neural nets, they have universal approximation properties that they, you make them bigger, and if you train them in the right way, they will converge. As you train them longer and you make the network bigger, they will converge to the true posterior. And so we have a fairly powerful tool here to approximate the Bayesian calculations that is not requiring the kind of assumptions that people have used in the past to simplify the calculations too much. And that leads to bad results with some of the Bayesian approaches. Okay, so for those who care about the math here, I'm going to try to be a little bit more concrete about the sort of Bayesian calculations we need to do. Let's denote by theta a theory and D a data set of XY pairs. So when we know a theory theta, we can predict Y given X. We can predict answer to a question X. Y is an answer, X is a question. So if we knew the theory, we would know what to do. And the probability of producing a particular answer is the likelihood for that question answer pair. We may also have a prior over theory, and we should, that says simpler theories are better. So using Bayes' rule and like very simple probabilistic calculations, you can show that the things you want to do are calculate the distribution over theories given the data. The thing you know is the data, and you want to know like which theory should I believe. And it's proportional to the prior P of theta times the likelihood P of D given theta. In other words, how does this theory fit the given data? Once you have that posterior, which is essentially trying to understand how the world works, the other thing you need to do is answer questions. So given a new question X, what is probability of different answers Y? And the thing you know, again, is the data set. Because you don't know what theory is correct, you have to sum over all the possible theories, and you get the summand here, which depends on the posterior we just calculated and something we know, which is the likelihood of a particular answer. So both calculations, the two lines here, are intractable. And I'm going to suggest that we can actually do that with some recent advances in neural nets. Yeah, I see that time is flying, so I'm going to skip some things. But the important bit here is we have a new generative slash reinforcement learning framework called generative flow networks that can train a neural net to sample from a distribution. So that's pi is the distribution that it's going to be learning, let's say over theories, such that the distribution it learns is going to be proportional to some given reward function, R of theta. So it's not like usual generative models where you give them a data set and they find a distribution that fits the data set. Here, you give them a function that evaluates how good a theory or how good the random variable is. So if you pick this function R to be the prior P of theta times the likelihood probability of the data given the theory, then your neural net will be trained to sample from the right thing, which is the posterior distribution. At least asymptotically, if you train it long enough and it's big enough, that's what it will do. So that's pretty exciting. And we've been doing a lot of work applying this already. In practice, what it means is we have a neural net that's going to spit out little pieces of a theory at a time. So here, the theory may be a causal graph. So a graph can be constructed one edge at a time. And so the neural net will take a partially specified theory and then spit out a new piece to add to the theory that will sample probabilistically, and then it will go on several times until it's happy that it has a good theory. I'm going to skip more things, but just use the last couple of minutes to tell you about how this is connected to a big discussion that is currently happening in the AI community about AI safety and the danger of AI systems that could be super intelligent and could somehow have their own goals that might not be well aligned with our goals as humans, which we have a hard time to express or we can't express perfectly well. And that potentially can create safety issues, which are similar to the difficulty, say, if with the genie's story and you're given 3 wishes and you spell your wishes, but somehow the genie is kind of doing something that was not what you expect. And maybe at the last wish you're asking to undo all the previous wishes. You have something with the story of the apprentice sorcerer, and if you've seen 2000 Space Odyssey, HAL 9000 is suffering from the same alignment problem. And the reason is the AI may interpret the goals we give it differently than the way we intend. And then it may generate sub-goals that could be harmful. Furthermore, if the AI is smarter than us, which is something that may happen in a few years or decades, we may not be able to stop it once it goes into these goals that are bad for us. So there's been around a decade of research in AI trying to deal with this, and we don't yet have an answer. But what's clear from that work is that the source of the problem is if the AI has agency, can do things in the world, and it can autonomously decide what it's going to do. And even if we give it goals, it's going to have its own goals to achieve the given goals. And that's this combination which gives rise to the safety issue. And so what I've been proposing recently, which you can find on my blog posts, is the idea of building an AI system that's more like a pure scientist, that would not have any agency, and so would be very safe, but at the same time could be like a scientist who understands the world, at least in some areas, better than us, and thus could be very useful to our human scientists. So again, the way to train that AI scientist would be essentially along the same lines as what I've talked about. One part of it is just like an understanding machine. It learns a posterior distribution over theories that explain the data. And the other part is a question answering machine, just like I explained, that exploits the understanding in order to come up with answers to questions. And I have a conjecture, I don't have a proof yet, that with this sort of training framework, there is no risk of loss of control from such a system. It cannot become suddenly autonomous. All right. If you want to learn more, in particular about the underlying machine learning methodology that I mentioned, the generative flow network, so GFlowNets, I wrote a tutorial, and my students and I have written like 15 papers already on this in the last couple of years at all of the major conferences. And you'll find a list of those papers and the tutorial there online. It should be easy to find. I'll stop here and be glad to answer your questions.
Thank you, Professor Bengio, for that interesting talk. And I'm getting some feedback. Can you hear me okay?
I do, but there's this extra noise. I don't know where it comes from.
So, yeah, I just wanted to open the floor to questions. So if anyone has any questions, you could place them in the chat. And I'll just kick off with one. So in your talk, you were you've applied the GFlow networks to this idea of constructing graphs for molecular biology, and I was wondering if you foresee any challenges in applying the GFlow networks to other domains, such as vision or text.
Yeah. So it's only in the last few months that we have come up with a version of the GFlowNets that handles continuous variables. So the original papers were all on discrete spaces. So graphs work, text would work, but now we're starting to work on the continuous domains. The other limit, I would say, is that the current algorithms, just like other reinforcement learning methods, they work well if the trajectories, like the number of decisions that have to be taken, is small-ish, like a few hundred. But if you want to do 1 million decisions, then it's probably not going to work in its current form. And in order to build this kind of AI scientist I was talking about, clearly you need to go there. So there's a question of how do we scale these things? And I have some ideas of to do that, but it's an open problem.
Okay. We have one question in the chat. Someone wants to know, how does active learning play into GFlow networks?
Yeah.
And can the learning process be sped up by allowing the model to choose the sequence of information it needs?
I didn't understand the second part, but I'll try to answer anyways.
Okay.
So yeah, active learning was the first application of GFlowNets. So the thing that's interesting about those generative models is that they will sample a very diverse set of candidates, like candidate theories, candidate molecules, more so than traditional methods like MCMC methods that tend to get stuck, like because of a sort of local optimum problem, or reinforcement learning, which wants to find a single solution, or traditional variational methods. There's also lots of connections between GFlowNets and variational methods, which also tend to get stuck in finding like one or very few solutions. So that's their main advantage, that diversity, and that diversity is very useful when you're doing active learning. If you're going to try some things on which you'd like to learn, you'd like those to be representative of the diversity of things that may be interesting to learn about. And I guess I didn't understand the second part, sorry.
So the second part was just about was essentially, I think, kind of rephrasing the question about could the learning process be sped up by letting the model actively request the examples that it needs.
Exactly. That's the whole point of active learning, indeed. I'm going to paste the tutorial link in the chat.
I think somebody already pasted it. It's okay.
Oh, okay, good.
Right. Another question from the chat: would an AI scientist approach require the model to have actuators that conduct experiments in the real world, or a simulation environment?
Well, that's a great question. If you want to be totally safe, no, you don't want that. And so, I mean, for total safety, you want humans in the loop here. So the AI scientists would propose things, and then humans would say yes or no, or do something else, and they would be the one doing things in the world, or like pressing the button to actually do experiments. So maybe we can get away with the machine actually acting in the world, but then I think that like proving that it's going to be safe is going to be harder. But I don't know. Like it's something that's open.
Right. And another question from the chat: how can we guarantee that everyone would follow the safety framework? I think that's not necessarily a question for you, but
but just about the previous question. It's like if you had a scientist that was also a politician, you could see there's some problems, potentially. Okay, so for how do we make sure everyone follows those guidelines, right? The problem is with even if we have a good recipe for building a safe AI system that's not going to blow in our face, how do we make sure everyone uses it? Yeah, this is this is hard. That's why I think we need legislation, international coordination, rules to make it not so easy. Like you need to register yourself if you build very powerful AI systems. It's all like a policy question, and I'm not an expert in this, but I think we need to have those discussions in the coming years.
Okay. Another question from the chat: the new approach separates the model and the world model and the question answering function. And does this open you to a criticism that the separation breaks the simplifying symmetry, having only one world model, and the world includes everything, including the questions and answers?
I don't see a problem there.
Mm-hmm.
I think that the model can include, the fact that the system exists in the world, because it's not acting in the world. But it's going to be a model. It's not going to be a perfect, that's what a model is about. It's an approximation of things. So I don't see a problem there.
Okay.
Which doesn't mean there isn't, but, I don't see it.
Right. And what would you say is the difference between the Bayesian posterior approach and taking the maximum likelihood estimate of a mixture model, which would use Bayes' rule?
That's very different.
Yeah.
Right. So a mixture model would still be a single model. It's just a richer model. but it could still be confidently wrong. And that's the thing that is actually dangerous, as I gave with my example with 2 doors, and you want to avoid in many applications. You don't want AI systems that are confidently wrong. It's like really dangerous. That you get the car accidents, right? Whereas the Bayesian thing would say, well, what's the most conservative thing I can do to avoid something really bad, knowing that there's uncertainty. That's what would be going on.
Right. And then another question is asking why compositional objects? Why not any objects?
Well, the advantage of taking something you want to generate, like a theory or a graph or something, or a vector of parameters, and breaking it down into components, and then generating each component at a time given the previous ones, like in autoregressive models, for example, is that you can represent much richer distributions. In fact, you can represent distributions that are like exponentially richer in the number of steps that you take. And so compositionality is like a huge source of expressiveness and also of generalization. And humans do that all the time. We try to break our understanding into small pieces, and we compose those pieces to come up with answers or explanations or whatever.
Right. And I think we're sort of at time, so I'll just have one more question. What would you like, or what is going to be your focus in the next 5 years while balancing, progressing the AI agenda and also, working on AI safety?
Yeah, this is a tough question, and I'm still thinking through this, but what I talked about today is pretty much the direction that I'd like to pursue, like at least on the technical side, like the AI side. What can we do to build AI systems that by themselves would be safe? And now humans could still misuse them, right? And make something unsafe with them. But at least if we can build powerful AI systems can help the world, whether it's medical or environment or education or whatever, that would be great. But it'd be even better if we know that when we build this machine, it's not going to suddenly do things we don't want.
Excellent. Okay, I think that's all we have time for. So I just wanted to thank you again for an excellent talk and presentation, and thank everyone for joining today.
Thank you, and thanks for the questions and the invitation.